All right, welcome back to probability modeling. I hope you had a good break. And let's go back into this and go back to lecturing. We got a few weeks ahead of us to finish the course. The plan for today is to complete chapter 3. We don't have that much left. And do chapter 4 as well, which is actually very short and more of an illustration than an actual chapter. So let's go. Let's start with a reminder of what we did last time. So the big thing we did last time was prove theorem 14, which said that in a Markov chain which is irreducible, strongly recurrent, positive recurrent, and aperiodic, then the distribution of the chain at time n converges to the unique stationary distribution. So this slide kind of breaks it into two. If the state space is finite, then you only need to check that the chain is irreducible, and then it's automatically positive recurrent. Then if you add aperiodic, then you will have convergence to the unique stationary distribution. If the state space is infinite, you need to check that it's positive recurrent by hand, which may or may not be very easy. Then you apply theorem 14 and you get your convergence to the unique stationary distribution. I want to add one new thing about null recurrent change. So last time we also proved that if, in the case of an infinite state space, if you're transient, then the distribution at time I converges to 0. Probability that time n, sorry. The probability that xn is I converges to 0. This is also true for null recurrent chains, as we give in this slide. So that's just what I said. Theorem, which was called theorem 11, applies to irreducible null recurrent chains. So if you're null recurrent, then the probability of being I at time n converges to 0. So for example, the simple random walk will do that on the integers. Okay, so that's what we know. This is everything about an irreducible chain. But what happens if you're not irreducible? So I want to talk about two cases. It's more of a guideline, so there's no theorems here. But it's good to understand what's going on. So consider a Markov chain which has only one closed class, but that closed class is not the whole space, which means we're not irreducible. So for example, imagine that there's one state, which is say state 1, which can lead into the other states which form a closed class, but we can't go back to that particular state 1. Then what happens is that you should think of what happens if we start inside the closed class. Then we're not going to leave it. And inside this, we have an irreducible Markov chain with a slightly smaller transition matrix, if you think of. And this one is irreducible and has a stationary distribution, as we know. And then you just need, if you want to find the stationary distribution for the whole Markov chain, you just need to assign 0 at the states which are outside of the closed class. And then we get the whole stationary distribution. So that's pretty simple. We're going to see an example with this actually very soon. And what about the case where there's 2 classes, for example, or even more, but let's stay with 2. If there's 2 or more positive recurrent closed classes, then it's kind of like what we said before. If you're in one of those classes, then you are a Markov chain which is irreducible, and we know what to do. You have a unique distribution. So we can understand what's going on inside each of those classes. So for example, one of the classes has invariant distribution pi, the other one has invariant distribution psi. And then it's actually fairly easy to see that the stationary distributions in general for this Markov chain can be written as combinations, convex combinations of pi and psi. So we get alpha pi plus 1 minus alpha psi, where pi and psi are those 2 stationary distributions. And this one is a stationary distribution. So you end up with a continuum course, of stationary distributions. So this is linked to something in linear algebra, really, because it means that this eigenvalue 1 has multiplicity more than 1. And so we can find more eigenvectors than just multiplying by a lambda. There's actually at least 2 independent eigenvectors. So maybe this seems a bit abstract, so let's just do an example of what happens in a non-irreducible chain. So let me show you the paper. All right, so I've drawn our matrix already. This matrix 1/3, 0, 0, 2/3, 0, 1, 0, 0, 0, 1/2, 1/2, 0, half, 0, 0, half. So what does this Markov chain look like? Well, we have our states 1, 2, 3, 4, and that's a weird way. It's not going to be very convenient, so let's do 1, 2, 4, and 3. You can go from 1 and stay at 1, so do a loop with probability 1/3, or I can go from 1 to 4 with probability 2/3. Meanwhile, 4 can go back to 1 or make a loop, both with probability half. You can see that 2 stays at 2 with probability 1, so this guy is a sink if you want. And then 3 can either go to 2 or loop around. So pretty simple Markov chain, and you'll notice that we actually have 2 Markov chains. We have 1 and 4, which form an irreducible class, and then 2 and 3, which another closed class, because we can't go back to 3 from 2. But yeah, so the thing to notice is that there's really 2 Markov chains, one for 1 and 4, and one for 2 and 3. So what happens if you try and find a stationary distribution? So let's try and solve the stationarity equations. Stationarity equations. That's an S. So, if you remember how this works, we get pi1 equals 1/3 of pi1 plus 1/2 of pi4. Pi2 equals pi2 plus 1/2 of pi3. Pi3 equals 1/2 of pi3, and pi4 is 2/3 pi1 plus 1/2 of pi4. Why is that? Remember that stationary means that if we start at the stationary and take a step, then we are still at the stationary distribution. So probability of being at pi1 is the same thing as of being at 1 is the same thing as either being at 1 and then staying, so pi1 and then this 1/3 for the loop, or first we were at 4 and then we went from 4 to 1, so this half. And this is easy to solve because you notice that this means that pi3 is 0, and so this equation gives us no extra information. Meanwhile, this one just gives us, so up pi4 is something like 4/3 of pi1. Yep. So we get pi3 equals 0, pi4 is 4/3 of pi1, and everything else is free. So we end up, remember we want that the sum of everything is 1, so we end up with 1 degree of freedom, and the solutions are of the form, let's say like this, 3/7 of 1 minus alpha, alpha, 0, 4/7 of 1 minus alpha. So what I did is parameterize things by pi2, because pi2 is free, and then notice that pi1 plus pi4 must be 1 minus alpha, and we know of course that pi4 must be 4/3 of pi1. So alpha is between 0 and 1. So notice that pi3 is 0. Pi3 is 0 because 3 is not in the closed class. So it's the first thing we said. If there are points which are outside of a closed class, so if we leave them, we can't go back, then they get assigned with 0 necessarily. Meanwhile, the other ones are in closed classes, so we can solve things the usual way. And as it happens, since there's in a sense 2 different chains, then we get one of them which has invariant measure 1, and the other one has 3/7, 4/7, and then we use the alpha to mix them up. Okay, so that's all I want to say about chains which are not irreducible. So now let's say a few things about another thing which is worth mentioning is periodicity. So periodicity, remember we said that things have to be aperiodic if you want convergence to your invariant distribution. So again, we're not going to present some kind of general theory about periodicity, but let's look at things on an example. So let's go back again to paper. And I will give you example 23. We're not even going to write the matrix this time. This example has a Markov chain with 3 states, 1, 2, and 3. And so 1 and 3, they always go towards 2 with probability 1, and then 2 will go to either 1 or 3 with probability 1/2. So it's very easy to see that this thing is irreducible. It's irreducible because, of course, you can go from anyone to anyone, no problem. And the period is 2. Because if you want to go back to your starting point, you need to make an even number of steps, and you can do it with exactly 2 steps. It's also not very hard to see that the invariant distribution pi is given by 1/4, 1/2, 1/4. So you can do it by hand, solve the equations, but it also kind of makes intuitive sense because you can see that somehow 2 should have twice the weight of the others, and by symmetry these 2 should have the same weight. And there you go. But in any case, you can solve your equations. But the question is, do we have that pi n, so the distribution at state n converges to that? Well, we don't. For example, if I take my initial distribution, pi 0, to be 1/2, 0, 1/2. So why do I do that? I'm saying I don't want to start at 2, but these 2 guys are really exchangeable, so I'm going to choose one of them arbitrarily, uniformly at random. If I take that, after 1 step, I'll end at 2, of course. So this means that pi 1 is 0, 1, 0. And then after another step, well, I'll be back, I'll have 1/2 on this side and 1/2 of the other side. So pi 2 is 1/2, 0, 1/2. And then pi 3, well, I'm at one of those, so I need to end up at 2. Pi 3 equals 0, 1, 0. And you can see what's going on. The sequence is periodic, so names make sense. Pi 3, so pi periodic with period 2, and we're going to cycle between 1/2, 0, 1/2 and 0, 1, 0. So we can't converge. And you could prove by induction that indeed we have exactly the sequence, and then pi n does not converge, unfortunately. Here periodicity gets in the way of theorem 24, unfortunately. Okay, so that's all we're going to say about periodicity. Now let's move on to the final section of chapter 3. which is we're going back to renewal processes. And what's going to happen is that Markov chain theory has some interesting things to say about renewal processes. So maybe you need to be reminded of the notations. So Fk is the distribution of the inter-renewal times. Fk is the probability that your waiting time has value k, and Uk is the probability that there is any renewal at time k. And d is the period of the whole thing, and mu is the average of your waiting time. So it's the average, is the expectation of a random variable with distribution Fk. And we're going to use Markov chain theory to get something interesting about our renewal process. So we're going to let xn be a random variable defined for time n, which is the number of steps we need until the next renewal. I call this the forward recurrence time. And number of steps, so in particular xn is 0 if there's a renewal at time n. I'll do a drawing to make this understandable. So let's have something like that. So remember, in the renewal process, we say that there is a renewal at time 0. So we're going to put n and xn here. So x0 is 0. And then there's going to be a first renewal time. Maybe the first waiting time is 5. So I'll put 1, 2, let's put our grid like that. 2, 3, 4, 5. So if the first renewal time is 5, then at time 1, I will jump to 4, because after 1 unit of time, I only need to wait 4 times. And then I'm going to just drop by 1 level every step like that. Because renewal, and then we need to wait 4, then we need to wait 3, then we need to wait 2, then we need to wait 1, then we need to wait 0. So we've reached our first renewal. This one didn't really count. And now a new random variable will get selected. Maybe this one was 3. So I'm going to jump to 2 here and then go back down. And then again, there's a new renewal. Maybe this time we chose a renewal time of 1, in which case I go back to 0 immediately. So what you see is that I have a process which makes somehow big jumps upwards and then goes down linearly, and then makes another jump and then goes down linearly. And maybe the next inter-renewal time was 6, in which case we'd make a jump of 5 and we'd reach here. Are these dots visible? I think these dots are visible. So this is my process xn. Let's go back to the slides. So the thing about this xn, so as I said, it either jumps high or goes down for by steps of -1. So if xn is equal to a certain number I, with I different from 0, then xn plus 1 will always be equal to I minus 1. The probability of xn plus 1 being I minus 1 given xn equals I is exactly 1, except in the case where I equals 0. So if we're given xn equals 0, this means we've hit a renewal, and then we're going to jump to level I if the renewal time is I plus 1. Because remember, because of the structure, we end up already waiting 1 unit. This is explained again, as I just said it. Xn equals 0 means there's a renewal, and xn plus 1 equals I means that the next renewal will occur if we wait I plus 1 units of time for the renewal. So that has probability fi plus 1. So this is a Markov chain. By by definition of your renewal process. And you can look at its transition matrix. It's a pretty simple transition matrix. So the fact that you always go down by 1 unit if you're not at 0 means that you've got this sub-diagonal of 1s like this. And then here you just have your jump probabilities. You get a matrix with a line of possibly non-zero numbers, this fake diagonal just below the actual diagonal of all ones, and the rest is 0. So the size of this matrix, so the state space is 0 to k minus 1, where k is the maximum possible value of a waiting time. But as you know, the waiting times can be infinite actually. That's not a problem at all for the theory, and in that case the matrix is actually infinite, and that is fine. But yeah, now we have a Markov chain, and we know its transition matrix, so hopefully we can use a theory node to find some new things. So here's some claims about this Markov chain. It's irreducible, so you can go anywhere. Well, remember that you can go back to 0 from any place just by going down, 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 and you can go from 0 to any place. Basically, well, you can go from 0 to the highest number k, and then from k you can reach any other number. So that's the simplest way to see. And this Markov chain will be positive recurrent if the renewal process is positive recurrent. So these two things have different definitions-ish, but remember, the renewal process is positive recurrent if its waiting time, the inter-renewal time, has finite expectation. This also happens to be the waiting time to 0, so things are fine and they are compatible. And you can even quite simply check that the stationary distribution is given by this thing. Probability of being an I is 1 over mu, mu being, remember, the average of your inter-renewal time, times 1 minus f1 minus f2, etc. minus fi. So the one which interests us the most is pi 0, which is just 1 over mu. And if the renewal process is transient or null recurrent, then the Markov chain is also transient or null recurrent. Null recurrent means the inter-renewal time has infinite expectation. And if you think about it, the inter-renewal time is exactly the return time to 0. So the return time to 0 has infinite expectation, which means null recurrent. And if it's transient, this means that you may not even come back to 0. There may not be a renewal. Same thing. And I guess xn isn't quite as well defined, but that's fine. That's fine. Okay, so we got corresponding properties. That's great. And so now we can have a thing called the renewal theorem, which is just an application of our convergence to our invariant distribution. So the theorem here is stated in the periodic case. Let's assume for a second that we're not periodic. So assume that this d is equal to 1. And so we get ud converges to 1 over mu. So 1 over mu is my invariant distribution at mu, and ud is the probability that un converges to 1 over mu. Un is the probability that there is a renewal at time n. So this is really good information. It tells you that the probability of having a renewal at a certain time actually converges to the inverse of the average of your waiting time. So that's in the positive recurrent case, where mu is properly defined and not infinite and positive. In the other cases, null recurrent or transient, un converges to 0. That's by our other theorem for the case of theorem 11, for the case of null recurrent or transient random walk. So great. There's a proof, but really there's not much to say about the proof. So d equals 1. Let's keep d equals 1 for a second. And then, as I said, un is the same thing as probability that xn equals 0. By theorem 14, this converges to pi 0, which is 1 over mu. And so we get what we want. And in the transient or null recurrence case, it tends to 0. Now, what about the periodic case? So periodic case, we only look at U indexed by ND, because we know that renewals can only happen at times which are multiples of D. And then it converges not to 1 over mu, but to D over mu. So good to know, remember that. And the proof, there is actually a proof. So for the periodic case, define a new renewal process. So new renewal process has a renewal at time n if the previous one had a renewal at time nd. So you kind of just rescale things slightly differently. And I will leave that as an exercise, that if you apply the theorem to the new process, then you get what we want. Because UND is a probability that the new one has a renewal at time n, so there's going to be factors of d coming out, and this is why you have a d here. Simple exercise. Okay, excellent. And we're going to end this, though, this very good theorem, by an application. And we're going to return to the example of Bernoulli trials with blocking. And actually, I don't have much to say about this, because it's going to be one of the cases of just magical use of the theorem solves a problem. So let's go back. So we're going to call this example 24. So Bernoulli trials with blocking. So it's a thing which was done before I even joined this course. Bernoulli trials with blocking. And you may remember or not, go back through your previous notes or look through the examples, that we had calculated that mu equals 1 plus p over p. So p was a factor between 0 and 1. And mu is the average of your inter-renewal time, which is not quite geometric because you block the possibility of a first renewal. And then we had proven that un converges to p divided by 1 plus p as n tends to infinity with a hard computation. Which I'm pretty sure involved taking power series and playing around with those. But here, of course, you notice that p over 1 minus p is the inverse of 1 plus p divided by p. I said minus, I wanted to say plus. Now, we can say that now we get un converges to 1 over mu directly with the renewal theorem. So that's great. This theorem lets us skip some of the hard maths we had to do before because we didn't have all the theory. That's one example of how Markov chains can be used to get some interesting things. And this ends chapter 3. So now you know a lot more about the long-run behavior of Markov chains, and we know that we converge to the invariant distribution, but periodicity can get in the way, though in the case of the renewal theorem, I did mention that sometimes there's ways around it. In any case, we are done with this chapter, and that is great. For the rest of this session, we're going to do the next chapter, which is very different I'm going to have a good time talking about new things. So, chapter 4 is called Google PageRank. So PageRank is a system of classifying web pages on the internet, which was used by Google to help their search engines. It's not really used nowadays anymore. Let's say it's less used, because in the age of social media, this modeling of the web they are using is not quite so good, but it's an excellent way of seeing that Markov chains have interesting uses in the real world. So let's see what we have. So PageRank can be seen as an algorithm used for ranking web pages in a search. So it measures what you can call the quality of a web page, and basically we say that a web page has a high quality if there's lots of links to it. So if it's easy to reach it while browsing. And this measure of quality is then used when you return the result of a search by putting high quality pages, by giving them priority in the results page if you want. And so the details about this were published in a paper by the founders of Google. So yeah, it's an interesting bit of history. So what do we have? So the idea is that we consider the web as a graph. The graph is made of all the web pages, and you're going to say that two pages are connected if there's a hyperlink between them. So they're connected if on one of those there's a link which you can click, which brings you to the other one. So first thing to remember, of course, to notice is that these things are directed. When there's a hyperlink which brings you from page A to page B, this might not be that there's a hyperlink going from page B to page A. And so we end up with something like that, maybe. So here's my graph. Here's my mini web, very simplified internet with 12 pages. And for example, page number 2 has a link going to page 11, has a link going to page 4, and that's all the links going out from page number 2. Meanwhile, there's links going in page number 2. They're coming from 3 and from 11. And that's how it works. So 4 has lots of stuff going in and has 1 going out to 3. And then, for example, some people like 5 have hyperlinks going out, but you can't reach 5 from another hyperlink. So good luck finding it. So you model your internet like that. So the internet, of course, is really big, but the same idea works. Instead, you just have billions of web pages instead of 12. Okay, so we have what we call a directed graph. And it's worth mentioning, we didn't have it in this example, but there may be several hyperlinks going from one page to another, because sometimes it's more convenient this way. Okay, so on this graph, you can define a random walk in ways which should remind you of things you know. And basically, you follow an arrow you follow a path by choosing an outward arrow uniformly when you are at a certain vertex. So choose any of the possible edges, each with the same probability, and then travel along it. You can think of it as a random surfer. That's a good way of thinking it. Random surfer, he is on a web page, and then on that web page he's going to see 7 hyperlinks. He clicks one at random, and then he's on a new page. He sees a number of hyperlinks. He chooses one at random, and so on. So you end up with a random walk with these transition probabilities. We'll go back to the example soon, but the probability of going from I to J is equal to the number of links between I and J divided by the total number of links leaving I. So if we go back here, for example, if I'm at 2, then 2 has 2 arrows leaving, one going to 4, one going to 11. So with probability half, I'll go to 11. With probability half, I'll go to 4. Let's say I go to 11. 11 has 1 arrow going out, it goes to 2, so I got no choice, I'm going to follow that. We're back at 2, half a chance of going there, half a chance of going there. Let's go to 4. 4 has only 1 arrow going out to 3, so you have no choice again. Let's go to 3. Then 3 has arrows going out to 2, 6, and 12, so you choose one of those with probability 3, and so 1/3, sorry, and so on and so forth. It gets written like this. So in this example, remember, there were no multiple arrows, but if there were, say, imagine there was an extra arrow from 3 to 12, then there'd be 4 arrows, and you choose this one, probability 1/4, this one, probability 1/4, this also 1/4, and this 1/4. So probability of going from 3 to 12 would be half. All right, so we've got this random walk, and there's one slight detail which doesn't matter much, but a random walk can get stuck if you end up on a page with no hyperlinks. So let's just assume that there is no such page, no page with no hyperlink. Otherwise, you can solve the problem by saying that if you end up at a dead end, you just restart again at a random spot. But we don't need to be bothered by this much at all. Okay, so this random walk happens to be a Markov chain, like things we've seen before, and we don't quite know if it's irreducible or aperiodic, but let's assume that it is. The internet is big, it's quite likely that you're aperiodic, and it's quite likely that the internet is irreducible. There's no two different distinct internets which you can't reach by hyperlinks. That sounds kind of far-fetched. Then by the previous chapter, we know that there's a unique stationary distribution. And in fact, the stationary distribution is the limit of the distribution at time n of your random surfer. So if the internet is big, it's going to take a long time to see this convergence, but it's still true. And this invariant stationary distribution, this is the rank. This is the page rank. We use those values as the rankings for our pages. So if pi j is big, then state j, web page number j, has a high PageRank value and is seen as a high quality page. Let's go back to our example here. So this graph, so you can write the equations for a stationary distribution. It's going to be a bit long because there's 12 equations. So good exercise if you really want to do this. You don't have to. And when you solve it, you end up with something like that. So here's the values of PageRank from like 12 pages. And so you'll notice something I mentioned before, that some of those have 0 value. That's because they're not part of a closed class. So if I'm at 10, I can exit to 3 and then never come back. If I'm at 5, I exit to 3 and never come back as well. So these guys get 0. These pages get 0. Meanwhile, the other ones get positive values. So you can see that if I restrict myself to the class 2, 3, 12, 6, 7, 4, 11, then you're properly irreducible. So it works. And you get the invariant distributions. One thing to notice is that more or less you will have a high rank if you have lots of arrows coming in, and a low rank if you have few arrows coming in. It's a good heuristic. It's not completely true, of course, but you see that 3 has 1, 2, 3, 4, 5 arrows coming in and has 1/3 of PageRank. 4 has 1, 2, 3, 4, 5 arrows coming in, has about 1/5, a bit more of arrows of PageRank. So even though these two don't really count, but these 3 arrows actually do count. Meanwhile, 11 has a low value because it's only linked to 2. And this is my PageRank. So if I had a search query and 11 and 3 both came out, then Google would rank 3 above 11 in the results page. That is PageRank in a nutshell. But there's a little bit more actually to say about this. We use a modification called damping. So what happens, which you might or might not notice as you browse on the internet, is that at some point you get bored and you decide that you don't want to keep following hyperlinks. So from time to time, the random surfer gives up following links, and instead you start again from a page which you choose totally randomly. And the way to do that is that we say that at any time with probability D, we keep following hyperlinks, but with probability 1 minus D, we start again at a random vertex, a random page. And as it happens, empirical data says that D is about 0.85. So when you're browsing and clicking links, you have a 15% probability of feeling that you don't want to click links anymore and you're going to start somewhere else. So of course, saying that the new page you start from is totally random is not the best approximation. It's probably a page I already know. I don't type random things in the address bar. But it's a first estimate. It's okay. And so we got new transition probabilities for your Markov chain. So these are the same as before, but now they're multiplied by 0.85. And then with a 0.15, you get a 1 over n for each page. Makes sense. Now, when you do that, the nice convenient thing about this damping thing, and was of course the total number of web pages, is that now we know that it's irreducible and aperiodic because there's a small probability of not moving. Starting again from a random page means you can actually start again from the same page. So if you're not moving, then you're aperiodic, and irreducible because I can go from anywhere to anywhere with a positive probability. And so by the theorem of Markov chains, we know that there's a unique stationary distribution pi, and we can use it to define the PageRank. And again, let's look at an example. So I've damped my random walk by 0.15. I get these new values for PageRank. Now you'll see that there are no points with 0 value. And the other values are usually slightly lower. What this damping does, it kind of homogenizes everything. And you'll see that the high values of PageRank have been slightly lowered. So let's compare with the previous tab. This was 1/3, and it's now 0.299. This 0.208 is now 0.192. Meanwhile, the zeros, which we had here, are all slightly increased. And that makes sense because we're now slightly less likely to visit those very popular pages, and we're slightly more likely to visit those very much not popular pages. The things are slightly squished together. And it's a more realistic way of looking at how a random surfer goes across the web. And this is PageRank. This is the introduction of PageRank. So PageRank is literally just assume that browsing the internet is a random walk. Then you get your Markov chain, take the invariant distribution, and that's your ranking. Of course, to find this invariant distribution, since the internet is huge, may take a lot of time to compute things, but you can do it. Google did it, apparently. And, they became what they are. And that was, yeah, that's going to be all for today. So this was the cultural cultural hour, if you wish, and a good way of getting back into things. On Friday, we'll go back to some more involved maths. I will see you then. Goodbye. And of course, if you have questions, you can send me some informal questions in the chat, or the best thing, if you got detailed questions about maths, wait for Friday for the office hour. Okay, thank you.